this is a video on how to prove the central limit theorem. The version of the central limit theorem that I'm going to use is already written up at the top, and the two facts below it in blue and green are some facts that we're going to need to prove the central limit theorem, but may not be on the top of your head. For this proof, this is the actual claim, but I actually prefer to use a slightly different version. So we're essentially trying to show that Sn minus mu times the square root n converges in distribution to normal 0 sigma, or sigma squared. This is the equivalent of saying Sn minus mu over sigma divided by square root n. This is equal to the sum I equals 1 to n xi over n minus n mu over n sigma over square root n, which is equal to the sum I equals 1 to n xi minus mu over n over sigma square root n, which is equal to 1 over square root n times the sum I equals 1 to n xi minus mu over sigma. So I'm going to go ahead and define yi as equaling xi minus mu over sigma, and then we want to show that yi the sum I equals 1 to n yi over square root n converges in distribution to normal 0, 1. Kind of just simplifies our situation a little bit and makes it easier to work with. I'm also going to define zi as, or sorry, not zi, zn equal to this summation so I don't have to keep writing that summation over and over again. So to prove this, we're actually going to use characteristic functions. If you don't know what characteristic functions, please pause the video and look that up. But if a distribution is equal in characteristic functions, then let me rephrase that. A characteristic distribution uniquely determines what the distribution is. So we're going to use characteristic functions. So the characteristic function of Zn is a function of t, which is equal to the expected value, exp it to the Zn. This is by definition of characteristic functions. Then we have the expected value, exp it, summation I equals 1 to n yi over square root n. And this is by the definition of Zn, so I haven't used anything special yet. Our next step is going to be expected value it y1 over square root n, expected value it over y2 over square root n, dot dot dot, all the way to yn over square root n. This is a property of exponents that we are using here. This is equivalent to the expected value, exp it y for any arbitrary I, square root n, to the power of n. Why we can do this, I'm actually going to put a little brackets over here just to make that explicit. We can do this because yi is independent of yj for all I not equal to j. So now we want to approximate this guy. We can approximate this guy using the fact that we have about up here with a Taylor series approximation to characteristic functions. So using that fact, this is approximately, well, our first component up here, you see we have a 1, and that's because when k equals 0, 0 factorial is 1, it to the power of 0 is 1, and exp, or expected value of x to the power of k for any random variable where k is equal to 0 is also 1. So our first term here is a 1. The next term, so how many components that we have of the Taylor series approximation depends on how many finite moments that we have. And right now, it's only given that we have the first two moments that are finite. That's given because of the settings. The expected value of x is finite, and the variance of x is finite. This means the expected value and the variance of y is finite. So we can only go up to 2 moments. So we have 1, which is moment 0. I'm not going to count that one. And then the next 2 components, because we know mean and variance are finite. So this becomes the expected value, yi to the power of 1, times it square root n to the power of 1 over 1 factorial plus the expected value of yi to the power of 2 times it square root n to the second power over 2 factorial, and then we're going to add t squared over n. And this whole component is to the power of n. So continuing on, first component is just 1. This second component is actually equal to, right here, is actually 0. So we don't have to worry about this guy at all. It's 0 because the expected value of y now has a mean value of 0 because expected value of x is mu. So expected value of y ends up being 0. Now, yi squared is equal to 1. Again, because we did this transformation, the variance of x is sigma squared, so the variance of y ends up being sigma squared over sigma squared, which is just 1. So we have 1 times, I is negative, so we have negative, the square root of negative 1, that squared ends up being just negative 1 times t squared over n over 2 plus t squared over n. Then we can simplify this a little bit. 1 plus negative t squared over 2 over n plus